Okay, so it's a pleasure to be here, and so I guess I'm a topologist who got mixed up with the wrong on hanging around number theory. And so this talk is somewhat topological. I'm looking for white chalk.
Oh, God, there's not white chalk. Well, we won't be able to have it.
I'll do it in red. No.
No white chalk?
No, it's not a single. It may be difficult to read on TV.
How about green chalk?
I can start in color. How about here's some yellow.
Yeah.
All right. I've got just this much chalk, but when I finish, I stop. Okay, so.
Professional organizer looking for chalk.
How about that?
Put it somewhere.
There goes your excuse.
So, this name, I think it's pretty well set in concrete, but if you have a better name, you can submit it. We haven't written anything. When I say we, it's joint with Francis Brown. And I should say that it's related to work of Benjamin and Enriquez on elliptic associators. Okay, so a basic question is, what is the genus 1 analog? Of an associator and the KZ associator, for example. And a second question is,
there's no excuse.
thank you. Good. So if there are such things, what do they tell us? What, if anything, do they tell us? That we don't already know. So let me talk a little bit about associators. So I wrote in the notes conceptual starting point. Right? So an associator, what is an associator? It's some sort of analog of a path in P1 minus 0, 1 and infinity from, I'll call it, say, V0, which is equal to ddx inside the tangent space of 0 of P0 to, say, V1 equal to minus ddx inside the tangent space of 1 of P1. Right?
Do you use the analog for paths or for homotopy class of paths?
Of a homotopy class of paths. Of a homotopy class. Of a class of paths. Okay, so I'll talk in more detail about tangential base points soon because I want to do some more exotic things with them. But, so here's a picture. There's P1C, this is P1R, P1C, and you'll have 0, 1, and infinity, and we have our tangent vectors here. Here's one of our tangent vectors, here's the other, and we might have some path that strays around and comes back here, right? So, and so the next important thing is that the path torso of P1 minus 0, 1, and infinity, and I guess I've got to specify my points. It's going to be exactly the 2 points or vertices I'm going to choose are going to be V0 and V1, right? And it's generated by just 3 paths. So here's 0, here's 1, and if I have this as a tangential base point, I've got to depart here with this velocity vector, return to it with minus that velocity vector, so that'd be gamma 0. And here I can do this guy here, I'll call this gamma 1, and then I have this path here, which some people call DCH. Right? So every homotopy class of paths in P1 that either starts or ends at one of these tangent vectors is a composition of these paths, right? And if you want to look at a motivic structure, say, I'll always work with unipotent fundamental groups, but you can do it with other fundamental groups. So, so the motivic, I'll put this in quotation marks, I'm just talking loosely here. So by this I mean mixed type structure or Galois action and so on say, pi unipotent inside P1 minus 0, 1, and infinity, say from V0 to V1 is, so this would be the path, philosophical paths from here to here. I could make these the same and take the pi 1, is determined by, basically by this guy here. Y is determined by how the Galois group or acts on or the periods of DCH. And that's because this loop here and this loop here both span a copy of Z of 1 or Q of 1. So log of gamma J span a copy of Q of 1. So it's, these guys aren't so interesting. I mean, they're needed and they're relevant, but this guy carries all the information. So, for example, if you're looking at periods, these guys, the logarithms of these have period 2 pi I. That's it. All right. So, so the KZ associator, I guess that's the same as the Drinfeld associator, is the regularized value of, I'm going to write it this way, I'll write it as, it's 1 plus the integral omega plus the integral omega omega plus evaluated on this path, the straight line path from 0 to 1. So this integral will, I should say, where omega is equal to dx over x times E0 plus dx over 1 minus x E1. So here, this guy here will lie inside C, power series in the non-commuting indeterminates E0 and E1. Okay? And this is just a logarithmic 1 form on P1 with values in, say, this algebra, or in fact in the Friedli algebra. So it's an element of omega 1 tempered with the Friedli algebra. And I don't need to put completion there. So, and its coefficients, as most people here know, are multiple zeta values, and you can make them motivic multi-zetas. All right, so that's the sort of context. So let me talk about what the genus 1 analog should be. I didn't bring my raincoat, so I'm going to... Okay, so genus 1. So we're going to be looking at M11. So up here I should say, let me write up something we realized relatively recently is that one thing that's confusing about this is that P1 minus 0, 1, and infinity plays two different roles in this theory. And you need to get your head around this a little bit. I mean, it makes a difference. You can think of it as the universal curve over the moduli space of 3 points on P1. And you say, that's pretty stupid. That's just, it could be spec Z or whatever. But it's also, so it's the universal curve of type 0, 3. But it's also P1 minus 0, 1, and infinity is equal to the moduli space of 4 points in P1.
Oh, it's much more natural that way. With the universal curve, there's no reason to remove the points.
No, I know you can get M04 over this, but conceptually, I'll try to point out at the end why I want to make that distinction. Because but anyway, so the way, so this guy here, so it's the moduli space of elliptic curves. So I'll think of this as the modular curve. And I'll think of it as SL2Z, it's the quotient of the upper half plane. Really, it's the Orbifold quotient. And so it's an Orbifold. And I really want to view it that way. Its fundamental group will be SL2Z. And it's got a natural base point. So there's a reason why with M04 or P1 minus 0 infinity, you just choose those 6 base points, because they're all the ones that are non-zero mod, they're the only base points that are mod P for all P. And so here, there's only 2. So I'll try to draw a picture. And these are plus or minus D, dq, which are in the tangent space at the cusp of M11 of, let's just write the Q disk. If you like, I could put M11 bar. But, so let's draw a picture. So there are various ways I could draw this. I want to draw the Q disk up here. Well, this is a neighborhood of 0.
Should the Q be like dq?
Sorry?
Do you really want d by dq or q d by dq?
I want d dq. I want an actual tangent vector. Right? So, I mean, for a limit mixed construct, you need a tangent vector. If you write q d dq doesn't depend on the coordinate. Right? So, anyway, so this, I draw these guys as cone. I never know how to draw this. This may be the orbit of I, and this may be the orbit of Rho, right? But we have our, there are only 2 natural, if you want to do things to work well over, say, the integers, there's only 2 tangent vectors you can choose here, d dq and minus d dq. Right? So, and so, so we'll look at pi 1 of M11, say with d dq, is naturally isomorphic to SL2Z. So, so one way to think of this is here's the upper half plane, here's the imaginary axis. If you map over to the Q disk, the imaginary axis here goes to this interval. And so you take this to be your contractible base point set, right? Because when we use a tangential base point, we're thinking of letting the base point go towards the cusp in the disk. Right? So, and this guy here, I want to think of, it's generated by S, which is equal to 0 minus 1, 1, 0, and T, which is equal to 1, 1, 0, 1. Right, so what is, so if I take T just corresponds to this loop here, just going around the cusp, and like in the case of P1, this guy here, log T, spans a copy of Q of 1. So we're going to complete the fundamental group in some fashion. When we do that, log T will generate a copy of Q of 1, and this guy here is the interesting guy here. Whoops.
So the pi 1 is in some kind of orbifold?
Sorry?
This is some kind of orbifold pi 1? I mean, M11 is contractible.
That's right, it says, so orbifold.
So the pi 1 also...
Yeah, I mean, what it means to work on the orbifold is essentially to work SL2 equivariantly on H. So people have been doing that
Okay.
for...
Just the definition of the symbol.
So, all right, and so what's the path corresponding to S, or what's a path? You can take, if you look at the imaginary axis and you go here, and there's something strange happens here, and you come back, this guy is a loop in this orbifold that corresponds to S here, corresponds to S under this. And so upstairs in the universal cover, what is it? It's the path joining 0 to infinity, right? That's a loop. So the generalization, so the genus 1 analog of DCH, the straight line path, is the imaginary axis. So that it represents an element of pi 1 with this tangential base point. And so again, like in genus 1, I'll talk a bit later about structure we can put here, but
I'm sorry, you mean the imaginary axis from pi to infinity, or from,
no, it'll be when you go, okay,
from 0 to infinity?
you can, it's going to be all the way from 0 to infinity. But it's the same as going down here, doing something here, and going back. We'll see that.
So that's what is the?
There, circle and come back.
Yeah, because S, if I is here, I takes this part and sends it up there.
Okay, I see. All right, so the loop there is the same as the straight line.
All right, so I wrote, the next section is called technical digression. It's not too bad, but so, I mean, we want to consider the SL2Z action, well, on pi 1 unipotent of an elliptic curve prime V. So I should just say the monodromy action here. So E is just an elliptic curve. And V is going to be an element of the tangent space of the identity of E, and E prime is just equal to E minus the identity. Okay, you might say, why didn't I take another point? There's a good reason for not taking another point. I want to take tangential base point as the identity. So I'm going to remove the identity, but as a base point for pi 1, I'm going to use some non-zero tangent vector. Non-zero. So for this, we need to understand two different things. We need to understand, so we're going to need two things. One, we're going to need M1 vector 1. So SL2Z doesn't really act on this. I need to take a larger group. So M11 is equal to the moduli space of EV, such EV, right? Elliptic curves and a non-zero tangent vector at the identity. We also, I think I need to explain tangential base points. So, all right, so M11 is actually easier to, M1 vector 1 is easier to work on, and it's sort of very familiar. It's just A2 minus the discriminant locus. It's the set of UV such that U squared is equal to 27, or U cubed, 27V squared. Right, so it's the plane minus this, and so UV, how does UV correspond to an elliptic curve with a non-zero tangent vector? Well, it corresponds to y squared equals 4x curved minus ux, ux minus v, and also the differential dx over y, which is an abelian differential, and then you just take the unique tangent vector such that dx over y evaluated on v is equal to 1, right? So, and this is not nasty. It's a scheme. It's a genuine space, so it's easier to work on. And this guy, in the sense of orbifold, actually is a C star bundle or a GM bundle to M11. So we're going to work on this guy, which is easier.
Are you inverting 6 or something?
Sorry?
Are you inverting 6? Yes.
Well, at the moment I'm really working. I'm going to do Q to RAM, so I only need work over Q. So this, yeah. So to do this, you need to invert 6. So, but we'll just do this over Q. Okay, and so what's its fundamental group? Okay, so fundamental group. Again, this is all very classical. Some base point into, say, pi 1 M11 with some base point. So this will be SL2Z. This guy here is in fact a braid group on 3 strings, and this is Z. Let me tell you what they are. This group has presentation SU such that S squared equals U cubed and S to the 4th equals 1. So this group here you can think of as SU such that S squared equals U cubed. And then this is the group generated by S to the 4th. Right? This is a central extension. And it's also the mapping class group of a surface with one genus 1 surface with one boundary component. So it's equal to gamma 1 vector 1. So diffeomorphisms of the surface that are isotopic classes of diffeomorphisms of the surface that are the identity on the boundary. All right, so let's talk about tangential base points. Okay, so sigma is equal to a surface, and I'll take P and Q in sigma, and sigma prime is going to be sigma minus P and Q, so you remove these guys, and we'll have, say, V element of TP sigma, and W in TQ sigma, and these are non-zero. And so let me just draw a picture here. I've got P and Q, and I've got a tangent vector here and a tangent vector here, and I want to say that a path from V to W is some path that starts initially with this velocity vector and arrives here with negative W as its tangent velocity vector, and it never passes through P or Q in the meantime. So this is okay, this is a definition, and then you can take the homotopy classes of such paths, but there's a better way to do this that Deline wrote down in his P1 paper, and there's a better way, and I want to exploit this to write down, say, the fiber of the universal elliptic curve over ddq. So that's why I'm doing this in detail. So I'm going to let sigma hat, a better way, it's an equivalent way of defining paths from this tangent vector to that one, but I'm going to let sigma hat be equal to the real oriented blow-up. I'll just write that BL plus as P and Q of sigma. So this is the real oriented blow-up. So just to be clear about what that is, so if you're at a point, you replace the point by all the oriented real directions of the point. So what happens if you blow up the disk at the origin? Take this at the disk, I claim this is just say 0, 1 cross the circle S1, and the map down to the disk would just take R theta, would just simply go down to RE to the I theta, right? So the oriented blow-up is just going to be an annulus. It replaces the point with the circle of directions at the point. And so then V and W will determine points. V and W are going to be in sigma hat. They're actually going to be in the boundary of sigma hat. So if I had a tangent vector here, it will determine that's the corresponding point in the boundary. And now you just define, so if you had some surface like this, and you have a tangent vector here and a tangent vector here, you would replace this by the surface with boundary here, and the two tangent vectors would get replaced by 2 points, and now a path from here, to here would just correspond to some path in here from this point to that point, right? So you can define the fundamental point, the tangential base points, by just looking at the genuine groupoid of this blown up surface.
So, I mean, what you said before, velocity vector, kind of worried me, because you're not really keeping track of the derivative.
Yeah, the velocity doesn't matter, provided you leave tangent to that and come back with it.
Right.
The point that's relevant is if you're trying to compute, if you've got some variation of mixed Todd structure over this, you're trying to compute the mixed Todd structure at this point, you need a tangent vector, right? And then the length of the tangent vector matters.
Yes, right.
So, Yeah, so I wrote down here, periods of, say, path torses with tangential base points are going to be limit mixed type structures. All right, so let's look at the first order Tate curve. So we've got the universal elliptic curve over M11, again in the orbifold sense. And now in here we have this tangent vector ddq, and I'd like to talk about the fiber eddq over of the universal elliptic curve over this guy here. And so so let me give you a topological model. So we've got so I'll be slightly sloppy here. This is the Tate curve. So over the disk, or just the universal elliptic curve on the disk. And what does this look like? Well, the central fibers are nodal cubic, and all the other fibers are smooth. So there it is there. This is the identity section. And this central fiber is just, this is just over Q, this is just P1 with 0 identified with infinity, and this point goes through at 1, right? So 0 and infinity get identified here. And so we can actually look at the universal elliptic curve over, say, over the punctured Q disk. I claim this extends to a nice family of topological family in a canonical way over the blow-up of this disk here. So how does this work? So it's clear how you restrict this family of elliptic curves here, and I have to fill it in when I blow up the disk. So here's the Q disk blowing up. I know how to define this family except on this inner circle here. So let me explain. This is the blowing up origin. This is the set of directions. So what I'm going to do here, let me point out, the topological picture of this is the following one. It's just P1 here. And say the identity is over here, and I've got this double point. And so what I'm going to do is I'm going to take the normalization of this and I'm going to blow up. So what I'm going to do is I'm going to take this real-oriented blow-up here. Right? There it is. This is blowing up P1. So this maybe corresponds to 0 and infinity, and I've still got 1 over here. And now this P1 has these 6 canonical tangent vectors. So there they are there. They're the corresponding points. And there's 2 ways I can join this up. Let me just draw, this might be the part of the real axis. This may be part of the real axis here. And I can either join up, so the real axis has 2 components or 1 component. In BDQ, so I'm going to join these together. So first of all, EDDQ, I just identify those so the red points match up. No twist, right?
Isn't 1 on the real axis?
Sorry?
Isn't 1 on the real axis?
Well, there's another part of the real. There it is.
These are on the negative part of the real axis.
Yeah, I drew. This is the negative. This is R negative. Thank you. All right. So. All right. And so this is the fiber over DDQ, is this guy here. What about over e to the I theta? What's another? So we just wrote, this is DDQ right here. If I did minus DDQ, I'd take a half twist, right? And if I do it over e to the I theta, what's the fiber over e to the I theta? I twist by theta, I actually twisted the bottom one to the right and glue. And that gives me the fiber. And you can write this down explicitly in equations. I did it in the notes on KZB equation. You can write it down explicitly, right? So I want to take this as the topological model of e dt. So the other thing you see here is that you have a map of P1 minus 0, 1, and infinity. This, say, 1 includes into e ddq 1, right? So this is the identity. You just see it here. P1 minus 0, 1, infinity, you just remove this guy here, and you remove, you know, you take the identity. So we've got this guy here, and then you can, it's technical that you can prove in the world of Hausdorff that on unipotent fundamental groups, that map there induces a map on unipotent pi 1s, which is everything, Galois equivariant, morphism with mixed Todd structures, and so on. So this is saying that if you can put such a structure on the unipotent fundamental group of e ddq, say minus its identity, it's got to be compatible with what's on P1 minus 0, 1, and infinity. But when we move up to the elliptic case, all of a sudden we acquire this large automorphism group, namely the mapping class group, the fundamental group of this module, basically an actual degree group. And this guy here. All right, so let's look at the unipotent fundamental group. So when we look at the unipotent fundamental group of ddq, so we're going to use the canonical tangent vector from P1, right? So P1 sitting inside it, we've got two canonical tangent vectors at 1, and I'll choose one of those. And so the Lie algebra so this is the fundamental group of this guy is free of rank 2. What is it? V. And I'll take the Durand fundamental group. There's a Lie algebra here, so this actually applies over Q. It's the completion of a free Lie algebra of rank 2, which I'll write like this. And so this is this thing actually over Q. So we also have that the Lie algebra of pi 1 unipotent of P1 minus 0, 1, and infinity with essentially the same base point, this guy over Q, is isomorphic to a free Lie algebra on this E0 and E1. Right? And so there's an induced map here, so we can write it down in the KZB equation. So this guy maps to this guy, so this guy will map to this guy. And the KZB equation, which is the genus 1 analog, or the elliptic KZB equation, which is the analog of KZ equation in genus 0, implies the following. It implies that this map here is that E0 goes to T over e to the T minus 1 times A. So this means adjoint action. And E1 so goes to T bracket A. And you can also, if you define E infinity, so E0 plus E1 plus E infinity is equal to 0. So E infinity goes to T over e to the minus T minus 1 times A. Right? So this is the map. It's So there's a canonical isomorph. This guy here is a canonical isomorphism.
Excuse me, this e to the t minus 1, t divided by t minus 1
Yeah.
is an element in the universal enveloping algebra generated by t and a.
Yeah.
And is it the element?
Sorry?
Is it the element?
Is it a Lie element?
The element.
I doubt it. I mean, this is just a word I think of as an enveloping algebra, and it's acting on this by the adjoint action. So, all right. So, oh yeah, and I want to give these guys names, so I don't have to write them down. I'm going to call this guy. I'll call this guy R0, R1, and I'll call this guy R infinity. They do add up to 0 if I did it. I think so, because you multiplied through by
No,
either.
that thing is 1 plus t, but t and a don't commute, I don't understand.
I think it's right. Well, these two are certainly right, and write down this one so they add up to 0. But it is, because I think you put multiply top and bottom by e to the t, and you'll put a 1 here, and that'll become.
With that part, the problem is that t and a don't commute.
Sorry?
In E0, the a is on the right. How do you? Oh, sorry, it's also on the right. I moved it in my notes.
Yeah.
They're both
I mean, this is t dot a. I could write it. It's okay. I'm sure it's right.
T dot a is.
Actually, I won't argue with because you think.
No, it's just, so it's not the commutators.
So do you mean commutator or do you mean?
This is adjoint action. So what's t to the
Oh,
n
that is
dot
adjoint.
a? It's equal to add t to the n of a.
Okay, so it's actually add t over e.
Yeah, that's what I said. And this is the adjoint action.
Then there's no problem.
You said adjoint, it wasn't clear whether you meant capital adjoint or lower adjoint.
Oh, I thought you meant country. I thought you thought I meant little add. Okay, so, all right, so we've got this guy here. And now let's try to understand Bevi to Duran. So, how can we think of, let's let EQ be equal to, so it's going to be C star mod Z to the Q. So what's a good way to think of this? You can think of it as the annulus here, and I'm going to take this, I'm going to make this the W plane, and this here is absolute value of W equal to 1 over the absolute value, square root of the absolute value of Q, and this will be W equals this, right? And then if you have a point W here, you identify it with Q times W in here, right? Now, what happens, so you take this annulus, and we ought to think too that our Q is approaching 0 along the positive real axis, right? So what happens if we let Q go to 0? This annulus here, this converges to the blow-up at the oriented blow-up at 0 and infinity of P1, right? And so, and when you're coming in on this axis, you're identifying the outer edge here with, you're identifying this edge here with this edge here with no rotation, right? So, and now we're also removing the identity. So what we're going to see is that E, D, DQ prime, I'm going to draw it like this. It's a disk here. This annulus is really this annulus here is the blow up here. This is infinity out here. This is 0. Well, this is the fiber over infinity. I'm also going to remove the disk here. I've blown up at 1 because I want to use tangential base point. And now, so we have all these things here. These are the sort of standard, this is the real axis in P1. And I have these loops here, and so this path here, if I go along here, I can write down phi of R infinity R0. And for this path here, I write down where phi is the Drinfeld associator, or the KZ associator, R0, R1. And if I go along this path here, I write down phi of R1, R infinity, right? And if I go around, so what I'm trying to do is write down the path torsor of this guy. If I go around here, this is around halfway around 0, I write down e to the I pi R0. Same on the bottom half. If I went around here, I'd write e to the I pi R1. And if I go this way up here, if I go on this blue part, I write down e to the plus I pi R infinity, right? So this tells us how to write. So if you have any path in our, and I've got one more thing to do. I've got green, good. Right, and so I've got to say that I'm identifying the outer and the inner path. So what happens if I go back here, and this edge gets identified with that? What do I write down? Got to get the right way. Going across this way, I write down e to the t. So this is the path torsor of the first order Tate curve, this guy here. Right? So if I want to write down, say, here's my two allowable base points are this guy here and this guy here. Nothing else is allowable, but suppose I want to write down a loop that goes out here, and then back here, around here, and here. I would write down this product, this guy here, times e to the t, times this guy here, times e to the minus I pi R0, times this guy here, and so on, right? So this gives me a map. And it's well defined by all the properties of associators. So later on I'll want to do this with any associator at all. I'm going to do it with the KZ associator or the Drinfeld associator. Whoa, time is flying. All right, so this gives a map. This gives so this gives a map from pi 1 of e d dq prime v. It gives a map into c, in fact into the group like it. I'll write this down. X, the complexified Lie algebra of a and t. Right? And in fact, all the coefficients of the monomials here, the coefficients, maybe I'll call this theta KZB. Coefficients are multi-zeta values. So, and this is unipotent completion. This map will induce an isomorphism of unipotent completions, because unipotent completion is functorial. If I have any automorphism of this group, it gives me an automorphism here, right? So I wrote down here major point, but the point is autos of pi 1 unipotent, the v prime ddq, give you autos of this guy here, and in particular its Lie algebra, which is LAT, right? So, as I explained before, SL2Z does not act on this guy because it doesn't preserve the base point. If you think of the elliptic curve, you can turn it sort of a quarter of a turn. It'll take the tangent vector and turn a quarter of a turn, right? So what you've got to do is you've got to lift S. So we're interested in S for reasons I explained before. We want to lift S to B3. There's various ways to explain this, but let me just explain it this way. You just take, I can think of my elliptic curve like this. is this identified, right? Squared. And the identity's in the middle. I rotate by pi over 2, and I get this guy here. But this is not the identity on the boundary. I've got to be in the mapping class group. So I take just here, so that's a nice sort of linear thing, but now I'm going to just imagine this is a sheet of rubber. I'm going to do nothing to the boundary and rotate this guy quarter turn back. So now just leave that where it is. Whoops. And now I rotated this back. So if I had a point here, this maybe was my base point, it became here, but I push it back up here. Turn it up.
Minus rotation by minus pi divided by 2.
Sorry?
Sorry.
I think it should be.
Minus this rotation.
Okay. No, I think this is right. Because there's all this business of left, right, and you've got to decide what's acting. I'm pretty sure this is right. Okay, so let me tell you what the modular inverter is. So the KZB-inverter. Okay, so so what's the point here? It's this S tilde. So I'm going to call this, I'll call this S tilde. This is an element of the braid group on 3 strings. And
But what's different from the S you had before?
sorry? Because this is in the braid group. So this
But you wrote V3 as generated by S and T, where S squared is U cubed. So it already had
yeah, it is. I'm not sure if there's a unique choice there, but
No, so you've written it that way, so it had an S. And this S is not that S?
well, I want to write it down as an actual diffeomorphism of the surface.
Okay.
Yeah, you can say. Okay, the KZB-inverter. So, so S twiddle induces C, which is going to take L A T into itself. And so I'm going to give you a formula for what it is. So, so definition. So, I want to define E to N. It's going to be a derivation of the Freely algebra generated by A and T. And so for n equals 0, it's going to be minus A d dt. And for n bigger than 0, it satisfies the following: epsilon 2n of t. These guys are actually very natural. It looks a bit strange when you see it the first time, but in terms of lots of things, they're basically uniquely determined. But it's going to be t to the 2n dot a, and it's characterized by the condition also that it vanish on t bracket a. So if you write down what it means for a derivation to act on this, you'll see that the value on t determines the value on a. And you can write down the formula. Okay, so these
Sorry, what just happened there? You said T is 2 to the minus 2.
Equal to 0.
yeah, this is again the adjoint little
Right,
a.
but what about E 2 and
Sorry, equals 0.
Oh, okay.
So it vanishes on. This corresponds to this diffeomorphism being the identity on the boundary
Yes.
of the surface. And in fact, the way things are here, the loop around the boundary is x of t bracket a. All right. So so there's some important things going on here. Just to give you an idea of the role these play, you've got the Dane twist. about the vanishing cycle. So my Tate curve is gone, but as you go around the inner loop of the blow up of the thing, you're rotating this identification, and that induces an automorphism of this elliptic curve, the Dane twist H, which takes ed dq prime into itself. And if you want a formula for what 1 over 2, so n is 1 over 2 pi I log h. Again, this turns out to be, by the KZB equation, this is the sum n greater than or equal to 0, 2n minus 1, b2n over 2n factorial times epsilon 2n. Okay? So this is the action of, so this is one of the generators of the braid group. It's a Dane twist around the vanishing cycle. And so I'm going to set omega equal to minus dq over q, epsilon 0 plus the sum n bigger than 1, 2 over 2n minus 2 factorial, g2n. So these are normalized Eisenstein series. This is normalized. Times dq over q times epsilon 2n. And so this you should think of, it's a form on omega 1, the q disk log 0, tensored with derivations on this guy here. And so we can, and in fact, this connection here, it's derived from the KZB equation, but this is FL2Z equivariant. Okay, and so what I'm going to let T is by definition the regularized value of 1 plus integral omega plus integral omega omega plus integral omega omega. So this is going to have coefficients which are iterated integrals of Eisenstein series. Back here I should point out these guys, there are lots of relations that hold by these, between these. There are Pollock relations. Every cusp form determines a countable number of independent relations between these guys here. And those guys are all, they're not Galois conjugates, so there's a huge number of relations between these guys. All right, but anyway, we've got this guy here on the path from I to infinity. So here's the imaginary axis. Here's 0, here's I infinity, here's I, and I'm going to take it on, let me get the direction correct. Yeah, this path here on alpha. So what's the formula for
Are you doing T or are you doing S?
sorry?
Are you doing S or are you doing T?
This is S. Oh, T, sorry, T here stands for the transport of,
Oh.
yeah, this is not, maybe I'll give it, what's another name? How about I'll call it F here. All right, so the formula here is, and so I'm going to let M be equal to I, 0 minus I, 1 over 2 pi I, and this is in SL2C. And so the theorem is that the modular inverter associated to KZB. So this is the one you start with the KZ connection. I wrote down the path torsor. You look at the endomorphism of S tilde, and now we write it down, it's going to be equal to F inverse MF times e to the 2 pi I add TA. And now,
You should be thinking about finishing.
okay, let me say, so there are properties you can write down of this. Maybe this satisfies, for example, a relation, which will be something like c squared equals c, I think I got this right here, e to the minus 2 pi I n cubed, for example. All right, so maybe I'll cut to the chase. Every associator phi gives an inverter C. I'll call it C sub phi. You just, when you write down the path torser upstairs, you just use this inverter instead of using the this associator instead of using the KZ. Yeah.
What is an inverter?
Well, we call it an inverter. You're perfectly welcome to send just another name because it's basically swapping A and B. And if you look at it in terms of Hodge theory, it's swapping a Q of 0 and a Q of 1. Maybe I'll try to make, yeah, so every one of these determines an inverter. So this is the kind of current.
So it's an element in this X plus this derivation in algebra which does what you are saying. So does this
Yeah, you start with the associator, and it'll give you a map from, if you like, pi 1 Betty into X of, well, pi 1 unipotent, the Betty version of this, into X of LA. And now if you take S tilde, it'll be an automorphism of this. If you're using the associator here to get to here, it'll just induce an automorphism here, which I'll call C phi. And it's not this, the KZB inverter has all sorts of properties. And maybe at the very end I'm going to make one remark about how it relates to Benjamin's work. But
I think we're getting kind of close to it.
okay, maybe I should, all right. So I'll just say all of the motivic guys here, if somehow you can move this guy around using, say, pi 1 of mixed Tate motives, satisfy all sorts of strong properties. It's not clear that all of these guys satisfy the same strong properties. So that's the point. I mean, there may be no way of determining. I'll put the conditions in the notes and maybe stop here.
Okay, just brief questions, if anyone has any brief questions. If you have a serious question, maybe you could ask it privately. We could
Only non-serious question.
allow,
the Grinfeld associator satisfies the pentagon and hexagon relation.
Yeah.
And they actually go into the definition of quantum group and everything. So the genus 1 associator, is there an analog of those two relations?
Yeah, I mean, put it, so the Pentagon equation, basically those relations are coming from topological facts about moduli spaces of curves of low dimension, right? So we're just trying to put that in here, and there's one other ingredient that, this relation here is such a relation, right? But the other thing is there's the relative completion, I'll call it G11, it also maps into the automorphism, maybe I'll put Durham, into L, A, T, hat. And now we've got a map of basically things coming from, say, GRT into here. So this is the relationship with Enriquez's work. So inside of this guy here is pi 1 of mixed Tate motives inside here. this guy normalizes this guy here. It's not clear that your GRT elliptic, the GRT, it also acts on this, whether it normalizes this. You know, you say, is the kernel of your thing the full braid group? A better way to say it would be, you should cut it down because the motivic guy's got to normalize the braid group part. And this, so it's somehow dealing with the same issue, but from a
Yes,
different
is the
point of
point
view.
that there are potentially extra relations.
Yeah.
There are new relations that may or may not be reducible from GRT.
Yeah, so maybe we call it a day.